Now let's see how we can prove the principle of induction using the well ordering principle. Now let S be a subset of natural numbers satisfying the conditions 1 belongs to S, and if n belongs to S, then n plus 1 belongs to S. Now we wish to prove that S is equal to n. We need to show that S is equal to n. Our proof will be based on a contradiction. That is, we will assume that S is not equal to n and obtain a contradiction using the well ordering principle. So, towards a proof of the fact S equals n, let us assume, suppose S is not equal to n. Because we have already started with a subset of n, S not equals n means there are some numbers, there are integers such that n does not belong to S. Now consider the set of all integers satisfying this condition. This is the set consisting of all natural numbers which does not belong to S. This set is denoted by n minus S. So this is the set of all natural numbers which does not belong to S. And from our assumption, it follows that this is a non-empty set. And indeed, it is a non-empty subset of natural numbers. Now, because this is a non-empty subset of natural numbers, we can apply the well ordering principle to this set. Now, what does the well ordering principle implies? It implies that this set should have a minimum element. So, we have n minus S consisting of all integers that does not belong to S, and we know this is a non-empty subset of natural numbers. Therefore, by the well ordering principle, n minus S has a minimum element. So let's call that minimum element n naught. What does that mean? That means, first of all, n naught belongs to n minus S, and for every n in n minus S, n is greater than or equal to n naught. Right. So n naught belongs to n minus S. Sorry, this should be n. The n does not belong to S. Right. So because n naught belongs to n minus S, that means n naught does not belong to S. But we already know 1 belongs to S. Because 1 belongs to S, n naught cannot be equal to 1. Therefore, n naught must be strictly larger than 1. Now, think of n naught minus 1. Because n naught is strictly larger than 1, n naught minus 1 is greater than 0, and it is an integer. But, so this is a positive integer, and hence this must be a natural number. Now, n naught is the minimum of S, n minus S. Therefore, n naught minus 1 cannot be a member of n minus S. Because n naught is the minimum of n minus S, n naught minus 1 does not belong to n minus S. Because this is a number smaller than the minimum of this set. From this we have that n naught minus 1 must belong to S. If it is an integer which does not belong to n minus S, then that means n naught minus 1 belongs to S. because otherwise n0 minus 1, if n0 minus 1 does not belong to S, implies that n0 minus 1 belongs to n minus S. Now, the second assumption about S tells us that if whenever an integer belongs to S, that integer plus 1 also belongs to S. By property 2, we have n0 minus 1 plus 1 also belongs to S. But this is equal to n0. So we have n0 belongs to S. Now note that we have already concluded that n0 does not belong to S. Now we have both n0 belongs to S and n0 does not belong to S, which is a contradiction. Now how did we obtain this contradiction? By assuming S is not equal to n. Therefore, we must have S is equal to n. Now let us recall what we have proved. We started with a set, a subset of natural numbers, satisfying the conditions 1 belongs to S, and if n belongs to S, then n plus 1 belongs to S. And we wanted to prove that S is equal to n. To prove this, we assume that S is not equal to n and considered all the integers which does not belong to S, all the natural numbers that does not belong to S. If S is not equal to n, this is going to be a non-empty set. And it is a subset of natural numbers. Then the well-ordering principle guarantees that S prime has a minimum. And because 1 belongs to S, this minimum cannot be equal to 1. Now, if we consider n0 minus 1, because n0 minus 1 is less than n0 and greater than 0, it is an integer, it is a natural number which does not belong to this set. Now, this does not belong to this set because this one is less than the minimum element of this set. This does not belong to this set, then it should violate this condition which determines the membership of this set, and therefore n0 minus 1 must belong to the set S. If n0 minus 1 belongs to S, from this condition we have that n0, then we have n0 minus 1 plus 1, which is equal to n0, also belongs to S. However, if n0 is the minimum of this set, then it must belong to this set, and therefore n0 cannot belong to S. Therefore, because n0 belongs to S prime, n0 does not belong to S. So we have a contradiction here because n0 belongs to S as well as n0 does not belong to S. This cannot happen, and therefore we have a contradiction. So this is a contradiction. Now how did we obtain this contradiction? By assuming that S is not equal to n. Therefore, from this we will conclude that S must be equal to n. So this completes the proof of the principle of induction using the well-ordering principle. Now there are several different variants of the principle of induction. Here PI means principle of induction. For example, consider the following statement. N squared is greater than 3 for every natural number n such that n is greater than or equal to 2. Of course, this is not true when n is equal to 1 because 1 squared is 1 which is less than 3. Note that we cannot apply the principle of induction to prove this, at least the one we have mentioned in the theorem, simply because this statement is not true when n is equal to 1, and therefore 1 does not belong to the set S given by this condition, that is the set of all integers such that n squared is greater than 3. However, it is clear that 2 belongs to this set, and we can also show without much trouble that if n plus n belongs to this set S, then n plus 1 also belongs to this set S. In other words, I cannot start the induction with n equals 1, but I have to start with n equals 2. So I can easily show that this is true for n equals 2 because 2 squared is equal to 4 is greater than 3. And for any n greater than 2, for n greater than or equal to 2, if n squared is greater than 3, then I can also show that n plus 1 squared, which is equal to n squared plus 2n plus 1, which is clearly greater than n squared, and therefore it is greater than 3. Now, from this, what do we establish? We can establish the fact that this is true for every integer greater than or equal to 2. Thus, we have n squared is greater than 3 for every n in n with the property that n is greater than or equal to 2. Now, in this case, the version of the principle of induction we need is the following one. Suppose we have a set S, a subset of natural numbers satisfying the conditions that 2 belongs to S, and if n belongs to S, then n plus 1 belongs to S. Then the conclusion that we want to make is that S must be equal to the set of all integers greater than or equal to 2. That is 2, 3, 4, so on and so forth. In fact, we can prove this using the well-ordering principle in exactly the same way did our previous proof. Now, there are several such variants of the principle of induction that comes handy when proving various results. We call all of these variants in general the principle of induction. Now, activity 6 outlines several different versions of the principle of induction. The first one is the following. Suppose we have a subset S of n with the property that for some integer n naught belongs to S, and for every integer n greater than n naught, if n belongs to S, then n plus 1 also belongs to S. Then the principle of induction in this case is that S contains all the integers which are greater than or equal to n naught. Another slight generalization of this one is the following, which extends to the set of integers. In this case, we have a subset of integers rather than a subset of natural numbers satisfying the following conditions. For some fixed n naught belongs to S, and for every integer greater than or equal to n naught, if n belongs to S, then we can show that n plus 1 also belongs to S. Then, the principle of induction guarantees that S is equal to the set of all integers greater than or equal to n naught. Now, for example, we can use this version of induction to prove some property is true for all integers greater than or equal to -1. One more version of the principle of induction is the following. Suppose we have a subset S of the natural numbers such that for some fixed n naught in n naught belongs to S. Moreover, if n is a natural number such that it is greater than n naught, and if we know the fact that n naught plus 1 all the way up to n belongs to S, then n naught plus 1 also belongs to S. So in other words, here this n0 is the base case, and if we know that all the numbers starting from n0 all the way up to n belongs to this set S, then the next number n plus 1 also belongs to S. Then the principle of induction in this case guarantees that S is equal to the set of all integers that are greater than or equal to n0. Now here is an important way to think about the induction principle. Now let's take this example. What this tells is that n0 belongs to S. And the second condition tells us that for every natural number greater than or equal to n0, if n belongs to S, then n plus 1 belongs to S. Now, if you start from this base case, what the second condition tells us is that because n0 belongs to S, n0 plus 1 belongs to S. And because n0 plus 1 belongs to S, we have n0 plus 2 belongs to S. And this continues forever. And hence, we have the set S equal to the set of all integers that are greater than or equal to n0. This case is similar to this, and the only difference is that instead of starting with a natural number n0, we have the option of starting this process with an integer n0, which can in general be less than or equal to 0. Again, n0 is going to be the base case, and we start with n0 and we have n0 plus 1, n0 plus 2, and so on and so forth in this set. In each cases, n0 is the smallest element of this set S. That's why we call this the base case. The third version of the principle of induction is slightly different, but essentially it gives the same result. Here we have n0 belongs to S. Now, the second condition implies that all the numbers from n0 all the way up to n belongs to S, then n plus 1 belongs to S. Now, because n0 belongs to S, all the numbers from n0 to n0 is there, therefore n0 plus 1 is in S. Because n0 and n0 plus 1 is there, n0 plus 2 is also there. Now, because n0, n0 plus 1 and n0 plus 2 is there, we have n0 plus 3 is there. Note that to conclude that the next integer is in this set, we are not only using the fact that n0 plus 3 is here, but the fact that all the integers starting from n0 all the way up to n0 plus 3 is in this set. And this process continues forever, but with a much stronger second condition. Again, the conclusion is that this set contains all the integers that are greater than or equal to n1. Now you can easily see that this can in fact replace by integers and still the same conclusion holds. Now we have already seen an example where we have to use a slightly different version of the basic induction principle. Let's look at another example where we have to use this version of induction, which we usually refer to as the strong induction. Suppose we wish to prove that every positive integer greater than 1 is a product of prime numbers. Even though we have not officially defined prime numbers yet in this course, I hope all of you know what a prime number is. A natural number n is called prime if it is not equal to 1 and its only divisors are 1 and itself. For example, 2 is a prime number because 2 is not equal to 1 and only divisors of 2 are 1 and 2. The next prime is 3. Now 4 is not a prime number because 4 is equal to 2 times 2 and therefore 2 divides 4 and therefore 4 has a divisor that is different from 1 and itself. Now 5 is a prime number because the only divisors of 5 are 1 and 5 is of course not equal to 1. Now let's look at this statement that every integer greater than 1 is a product of prime numbers. Say every positive integer n is a product of prime numbers p1, p2 up to pk. Here, a product can mean just k equals 1, in which case there is only one prime. This essentially means that n is a prime. Now let us prove this by induction. Our base case is going to be n equals 2. In this case, 2 is already a prime, and therefore it is a product of primes in the trivial way with k equals 1. Now let's suppose this is true for n. Suppose this is true for n, and try to prove that the result must also be true for n plus 1. Say that n is a product of primes p1, p2 up to pk, of course with the possibility that k is equal to 1. Now using this we wish to prove that n plus 1 is also a product of primes. So there are two cases we have to consider here. The first case is n plus 1 itself is a prime, and the second case is that n plus 1 is not a prime. If n plus 1 is a prime, then n plus 1 is already a product of primes, because it is n plus 1 is equal to n plus 1, and we are just choosing k equals 1 here, is already a product of primes. The more interesting situation is when n plus 1 is not a prime. If n plus 1 is not a prime, then it must be the product of two integers a, b, with the property that a and b are greater than 1 and less than n plus 1. Because n plus 1 will now have a divisor which is different from 1 and itself. Therefore, one of these it has a factor which is greater than 1 and less than n plus 1, and then the other one should also be greater than 1 and less than n plus 1. Now, there is a small issue in applying our hypothesis to this case, because we only know that a and b are less than n plus 1 and greater than 1. If one of a or b equals n, then we could have applied the inductive hypothesis and concluded that a or b is a product of prime numbers. However, in this case, we can't guarantee that a or b is equal to n. However, I hope all of you can see that there is no harm in assuming this result is true for all integers greater than 1 and less than or equal. In that case, we know a is one of such integers and b is also another such integer, and therefore each a and b is a product of prime numbers. Therefore, let's change this hypothesis into the following. I'm going to erase this. I'm going to assume that for every integer n such that m is greater than 1 and less than or equal n, I have n is a product of prime numbers. In other words, I am assuming the result is true for all integers greater than 1 and less than or equal n. Now, I can immediately apply my assumption to a and b, because a is greater than 1 and less than or equal n. If a is less than n plus 1, then it must be less than or equal n. I have a is a product of prime numbers, p1, p2 up to pk, and b is also greater than 1 and less than or equal n, and therefore b is also a product of prime numbers. Now from this, we may conclude with the help of the strong induction that the result is true for all n greater than 1. In other words, every integer n greater than 1 is a product of prime numbers. I have given a complete proof of this in the handout. Please go through this again and try to understand how the principle of strong induction becomes relevant and why it is important in proving certain results. Now coming back to activity 6, I am going to leave the proof of these versions for you. I am just going to summarize two main versions of the inductive principle. So these are the induction and the strong induction. Consider a statement Pn where n belongs to n. The principle of induction is the following. If we can show P1 is true, and for every natural number n, if Pn is true, then Pn plus 1 is also true. Then the principle of induction guarantees that Pn is true for all natural numbers. In the second version of the principle of induction, which we usually refer to as strong induction, we have the following. P1 is true, and for every natural number, if P1 up to Pn is true, then Pn plus 1 is also true. If we have these two conditions, then the principle of strong induction guarantees that Pn is true for all natural numbers. Now here are two more examples for you to try. The first one is similar to what we have already seen, and you can prove this using the principle of strong induction. The second one is a bit more involved. I encourage you to try this and compare your solution with the one I have given in the handout. Next, I am going to describe one more version of the principle of induction. For that, I want to look at the next example. Now, here is a formula which allows us to compute the nth Fibonacci number directly without using the recursive definition. Let us try to prove this using the principle of induction. In other words, we wish to prove that Fn equals this for every natural number n. If we wish to prove this using the principle of induction, we would try to first prove this for n equals 1. In this case, f of 1 is equal to 1 over square root 5 times 1 plus square root 5 over 2 minus 1 minus square root 5 over 2 which is equal to 1. Now, in the inductive step, we wish to establish this result for f n plus 1, assuming some prior results. Because fn plus 1 is equal to fn plus fn minus 1, it is clear that we cannot use the simple induction. Instead, we may consider using the strong induction. So let us assume that the result is true for all integers up to n. So I am going to assume the result is true for all integers 1 through n. Then it is indeed the case that fn is equal to 1 over root 5 times 1 plus root 5 over 2 to the nth power minus 1 minus root 5 over 2 to the nth power plus, and now n minus, this result is also true for n minus 1, and therefore I can write this is equal to 1 over root 5 1 plus root 5 over 2 to the n minus first power minus 1 minus root 5 over 2 to the n minus first power. And with little bit of effort, by simplifying these expressions, you can easily obtain that this is equal to 1 over root 5 times 1 plus root 5 over 2 to the n plus first power minus 1 plus root 5 over 2 to the n plus first power. sorry, this should be 1 minus. Now you might think that the principle of strong induction implies that this result is true for all integers. However, I claim there is a small issue in this proof. To understand why, let us see what is happening a bit more carefully. We know the result is true for n equals 1. However, note that the result does not follow for n equals 2 just because of the case that it is true for f1. The reason for this is that f2 was defined independently without using this recursive formula. Therefore, for this proof to be valid, we should also establish this result for n equals 2 independently from the case n equals 1. Now I am going to leave for you to verify that this is indeed the case when n is equal to 2. Now if we have established the result for n equals 1 and n equals 2, and also if we can prove that if it is the case for fn and fn minus 1, then it is also true for fn plus 1, then from the principle of induction we have this result for every n in f. Now this version of the principle of induction is particularly useful when we have to prove facts about recursively defined of things. Now let us recall what a recursive definition is. First, let us look at some examples of an inductive definition. Note that triangular numbers that are defined for every natural number n can be defined inductively or recursively as follows. We set t1 to be equal to 1, and then we give a recursive formula which enables us to compute the next triangular number using the triangular number that we already know. So the n triangular number is equal to the n minus first triangular number plus n. So we set t1 equals 1 and tn equals tn minus 1 plus n. This recursive definition enables us to compute all the triangular numbers starting from the initial case. T2 will be the previous triangular number plus n is equal to 2, which is 3. T3 will be T2 plus T3, that is 3 plus 3, which is 6. And if I write one more term, T4 is equal to T3 plus 4, which is 6 plus 4, which is equal to 10. Now we call this a recursive or an inductive definition of triangular numbers. Similarly, pentagonal numbers can be defined inductively or recursively by declaring P1 to be equal 1 and Pn, the nth pentagonal number, equals the n minus first pentagonal number, that is the one before Pn, plus 3n minus 2. Note that this recursive formula is valid for n greater than or equal to 2, because for the case n equals 1, we have to use the base case to compute the first pentagonal number. Now in the case of Fibonacci numbers, we know that there are two base cases, f1 and f2 are defined independently, and we have set them equal to 1. But for n greater than or equal to 3, we set the nth Fibonacci number equal to the sum of the two previous Fibonacci numbers. We have already seen this example and have used this definition to compute various things about Fibonacci numbers. Here's one more example we have already seen. The Catalan numbers are defined recursively by setting the 0th Catalan number equals 1, and for n greater than or equal to 1 in this case, because we have the case 0 here, and therefore the next integer is 1. Right. For n greater than or equal to 1, we have the nth Catalan number equals this formula which enables us to compute the nth Catalan number using the n minus first Catalan number. Here is the general framework for an inductive definition. Let A be an integer, and suppose I want to define some values fa, fa1, fa plus 1, fa plus 2, and so on and so forth. So this is same as defining a function with the domain a plus 1, a plus 2, and so on and so forth. Now one way to define such a function is to first declare some initial values of this function that I can compute directly. Let's say I want to set fa equals 3, fa plus 1 equals 4, and fa plus 2 equals 0. Now this will be our base case. Next I am going to give a rule which enables us to compute the remaining terms using the values that are already known to us. For example, I can say if I know the values fn plus 1 and fn plus 2, then I can tell how to compute the next term, which is fn plus 3. I'm going to tell, for example, let's say fn plus 3 can be computed using these three values using the following recipe. I'm going to take fn plus 2 times fn plus 1 plus fn. We call this a recursive formula for f. Let's see how we can compute the rest of the function values using this recursive formula. I already know fa plus 1 and fa plus 2. Now my goal is to compute fa plus 3. fa plus 3 is equal to fa plus 2 times fa plus 1 plus fa. Now I already know these values given by the base cases, and therefore I simply plug these values and compute fa plus 3. So this is 0 times 4 plus 3, which is equal to 3. To compute fa plus 4, it is equal to, this is the case where n is equal to a plus 1. So I have to use the two previous values, fa plus 3 times fa plus 2. I obtain this by substituting n equals a plus 1. So I have a plus 1 plus 2, that is a plus 3. Then I have a plus 2 plus f of a plus 1. So this is by substituting n equals a plus 1. This is when n is equal to a. Now this is equal to 3 times 0 plus 4, which is 4. Now the next term, fa plus 5, can be computed by substituting n equals a plus 2. Now I obtain f, this is f of a plus 4. So either you can substitute n equals a plus 2, or just remember the idea of the recursive formula. I just take the product of the two immediate terms plus the term before these two terms. So that is a plus 4 times f of a plus 3 times f of a plus 2. This gives me 4 times 3 plus 0, which is 12. Now this process continues, and for any integer in this set, I can compute the function value at that integer by continuing this process until I reach that integer. I hope it is clear to everybody why these three initial conditions and this recursive formula defines a well-defined function with these numbers, integers, being the domain of this function. We say these three initial conditions and this recursive formula an inductive or a recursive definition of this function f. Here is the general definition. Let a be a whole number and x be the subset of w consisting of all integers greater than or equal to x. So x is the set which contains all integers or all whole numbers that are greater than or equal to x. To define a function with x being the domain using a recursive or inductive rule, we first declare some base values fa plus 1 up to fa plus k minus 1. So these are k many initial values for some integer k. this is the first initial value, this is the second initial value, and you see that for the kth initial value, we must have a plus k minus 1. Then we give a recursive formula that enables us to compute fn from the k preceding values. That is to say, how to compute fn using fn minus 1, fn minus 2, all the way up to fn minus k. So this is some rule that uses these values. Therefore, I can in general write it in this form. So this is some function of these values. However, note that this recursive formula can be used only to compute function values for n greater than or equal to a plus k. If n is less than a plus k and greater than or equal to a, then the function values are given by the k initial values of the function f. How can we use induction or the principle of induction to prove things about a function that is defined inductively or recursively? Suppose I want to show that fn holds the property Cn. For example, let's say I want to prove fn is even for every n, or maybe something like this, even an explicit formula, fn is equal to into the n plus 1 for every n. In fact, this should be n greater than or equal a, and here also for every n greater than or equal to a. N is a integer. Now consider the function we defined recursively in the previous slide. So this function is defined on the domain f and the domain x, consisting of all integers that are greater than or equal to a. Here a is some whole number, or it can be even an integer, where the function was defined recursively by declaring some k initial values and giving a recursive formula to compute fn using the k previous values. So let's call this formula f. So it uses fn minus 1 all the way up to fn minus k. Here n must be greater than or equal to a plus k, because this recursive formula is valid only if n is greater than these k base cases. So that means n must be greater than a plus k minus 1. Therefore, a is greater than or n is greater than or equal to a plus k minus 1. So this is same as saying n is greater than a plus k minus 1, because n is an integer. I want to prove that fn satisfies some condition Pn. I may want to prove that fn is equal to 2 to the n plus 1, or even fn is even, because here n must be greater than or equal to a. Now this statement fn equals 2 to the n plus 1, or the statement fn is even, is the property that we wish to prove. So that is what we identify by Pn. The version of induction that enables us to prove something like this for an inductively defined function is the following. The base case of the induction is the k initial values. That is, we have to show that Pi is true for I equals a plus 1 all the way up to a plus k minus 1. Remember, these are the k initial cases. The first thing is to show that whatever the statement is valid for n equals a plus 1 all the way up to n equals a plus k minus 1. In the inductive step, we assume that this statement is true for k consecutive values of n. That is, we suppose, let's take k consecutive values of n plus 1, n plus 2, all the way up to n plus k minus 1. See, the first one is n, second one is n plus 1, third one is n plus 2, therefore the kth one must be n plus k minus 1. We assume Pn plus 1, Pn plus 2, all the way up to Pn plus k minus 1 are true. Then, with assuming this, we will prove that for the next value of n, that is n plus k, p is true. That is p n plus k is true. Note that here n must be greater than or equal to n. If we can prove this, then the inductive principle guarantees that Pn holds for all integers n greater than or equal to n. Now to summarize, the base case consists of showing Pi holds for I equals a plus 1, all the way up to a plus k minus 1, and the inductive step is to use the recurrence to show that for n greater than or equal to a, if Fn satisfies Pn, if n plus 1 satisfies Pn plus 1, all the way up to Fn plus k minus 1 satisfies the condition Pn plus k minus 1. Then, using this assumption and the recurrence, if we can show that Fn plus k also satisfies the condition Pn plus k, then the principle of induction guarantees that this property Pn is held by Fn for every n greater than or equal to n. We have already seen an example of this version of induction where we used it to prove some property of Fibonacci numbers. Here is another example. Consider the following definition of f with domain being natural numbers, where f of 1 is equal to 1, f of 2 is equal to 3, and f of 3 is equal to 5. So I have f of 1 equals 1, f of 2 equals 3, and f of 3 equals 5. Then, to compute values of this function for n greater than 3, I have the recursive rule that tells me f of n is equal to the sum of the three previous values. That is fn minus 1 plus fn minus 2 plus fn minus 3. Now suppose I want to prove the statement that fn is odd for all n belongs to f. How would I prove this using induction? First I have to verify that f of 1 is odd, f of 2 is odd, and f of 3 is odd. Then, for the inductive step, I assume that f of n minus 1, f of n minus 2, and f of n minus 3 are odd, and show that if these three numbers are odd, then f of n must also be an odd one. Let's do this. Alright, three base cases are n equals 1, n equals 2, and n equals 3. Now clearly, for these cases, f1 is equal to 1, and therefore f1 is odd. For the second case, f2 is equal to 3, and therefore f2 is also odd. And for the case n equals 3, f3 is 5, and clearly f3 is also odd. Now we have checked the three base cases and verified that this statement is indeed true for these base cases. In our inductive step, let us assume this is true for three consecutive values of n. That is to say, fn, fn plus 1, and fn plus 2 are odd. From this assumption, let us now prove that fn plus 3 is also odd. Now, fn plus 3 can be written in terms of fn plus 2, and fn plus 1, and fn using the recursive formula. Fn plus 3 is equal to fn plus 2 plus fn plus 1 plus fn. Now note that we have assumed these are odd numbers. Now if we add two odd numbers, we get an even number. And if we add an even number to odd number, we get an odd number. It's even, and therefore fn plus 2 plus fn plus 1 plus fn is odd because this part is an even number and this is an odd number. This whole thing is equal to fn plus 3. So what have we done? We have shown that fn plus 3 is also an odd number. Now we can appeal to principle of induction and conclude that fn is odd for all n in F. I hope now you can try activity 7 on your own. Activity 8 is also a fun problem to try. You can apply a recursive definition to solve this problem. I'm going to leave this for you to try. This will be the conclusion of the first session of the second lesson. In my next video, I'm going to give a brief introduction to the absolute value and two more functions called the flow and the series. Till I meet you with the next video, please go through the handout and try to understand the examples, and please try to complete the given activities. Stay well and stay safe.